Vortex shedding, or von Karman shedding, is a phenomenon named after Hungarian-born mathematician, physicist, aeronautical engineer Theodor von Karman. He was a professor at Caltech and eventually helped to found JPL. This project looked to study the effects of Reynolds number on vortex shedding, specifically for an infinite cylinder. The motivation behind this was to look at how geometry of a structure could cause it to fail when placed into a flow field. It was originally thought that vortex shedding led to a failure of the Tacoma Narrows Bridge in 1940. This was disproven. Vortex shedding was found to be the cause of failure for a tower of the Vertigo roller coaster at Cedar Point in Ohio. The 2D system was modeled in ANSYS as a surface. The flow domain was a 30 by 15 meter box with a 1 meter diameter circle placed 16 meters from the inlet and 7.5 meters from each no-shear wall. Boundary conditions were set to a constant velocity in the x direction, outlet pressure set to 0 pascals, no shear condition at walls of the domain. The disk cylinder has a no-slip condition to induce drag vortices. Constant. In order to study the effect of Reynolds number, viscosity and density were held constant. This meant Reynolds number was entirely dependent on flow velocity. Velocity was run from 20 meters per second up to 240 meters per second. The vortex potential equation is the main governing equation for this phenomenon. This satisfies conservation of mass and momentum. This also satisfies Laplace's equation in 2D. Velocity equations are converted to cylindrical coordinates, and for 2D flow, del cross V must be equal to 0. For the 2D case, all z derivatives are 0. Is that fine? Vortex strength is a constant value calculated by the surface integral of velocity around a contour. ds is the differential length around the contour. Vortices are controlled by Reynolds number. Sources gave that the range of shedding should occur between a Reynolds number of 40 to 150. Frequency of the shedding can be backed out of the Struhel number. The 2D sketch was meshed in ANSYS. A coarse triangle mesh was used in the far field. Around the cylinder, the mesh was refined with an inflation feature of 40 layers, the first layer having a height of 0.025 meters. This increased radially. The simple pressure correction method was used to solve the transient problem. Time step size was 0.01 seconds, and the solution was run for a total of 250 time steps. The laminar viscous model was used. Other methods were explored but significantly increased computing time. Results did not change much. The following videos show results for a Reynolds number of 80 and Reynolds number of 240. In 80, vortex shedding is visible by both pressure and velocity contour plots as an increase in velocity, decrease in pressure. For the Reynolds number of 240, flow is uniform and no vortex shedding is shown. Pressure and velocity distributions develop early and do not change over time once fully developed. Lift coefficients can be compared to show how lift forces could be potentially destructive when vortices are shed. Residuals were compared as well, but being a constantly changing transient solution, the residuals don't actually tell us much about the solution. Vortex shedding was reproduced for velocities between 75 and 175 meters per second. Below and above these values, vortex shedding was not occurring. Vortex shedding manifests itself as a local increase in velocity and decrease in pressure. Von Karman found that the ratio of vertical separation and staggered distance of the vortices should be 0.2806. This was not verified and would be an interesting subject to study further.